A switch snaps shut and a light should glow. Now stretch the scene to the edge of absurd. 2 wires, each 300,000 kilometers long, run out and back while the bulb sits 1 meter from the battery. The circuit is ideal. The wires have no resistance, and the bulb turns on the instant power can reach it. So when does it light? Many minds jump to 1 second because that is how far light travels. But this puzzle is not about electrons racing through copper. It is about fields spreading through the space around the wires and energy following that change. The moon-long wire puzzle. Picture a giant loop made of a battery, a switch, a bulb, and 2 absurdly long wires. Each wire is 300,000 kilometers long. So each one is 1 light second in length. They run away, reach far into space, and come back to meet a bulb sitting just 1 meter from the battery. The rules are simplified. The wires have no resistance, so they do not waste energy as heat. The bulb is magic in one narrow way. The instant useful electrical power reaches it. It emits light with no warm-up. With those rules, the only real question is timing. Most instincts say the bulb must wait for something to arrive along the copper. So, a second sounds reasonable. Some will guess half a second, thinking the change only needs to reach the bulb end of the loop. Others may say 2 seconds, imagining a full round trip. But those guesses quietly assume that electricity is a substance that must travel the entire path first. In reality, closing the switch changes the electric field pattern around the circuit, and that change propagates. The long wires do matter, but they are not the 1 meter shortcut's main limit. The fastest thing in the story is not a drifting electron. It is the electromagnetic disturbance that spreads through space. The story about electrons that breaks down. A common classroom picture treats power lines like a clear plastic tube, and electrons like a linked chain inside it. A generator pushes and pulls the chain 60 times a second. And a toaster uses the energy because electrons squeeze through the hot element and dump their energy as heat. The picture feels friendly, and it helps people accept alternating current where charge sloshes back and forth instead of streaming one way. The trouble is that key parts of the real grid do not match the story. There is not one unbroken piece of conducting metal running from a power station to a kitchen. Transformers sit everywhere and inside a transformer. One coil is wrapped on one side while a different coil is wrapped on the other side. Between them is insulation, sometimes air, and often a core that guides magnetism. Electrons in one coil do not hop the gap to the other coil in normal operation. That single fact already shows that the same electrons cannot be the couriers that deliver energy across the whole system. The two-way motion of current in AC creates another puzzle. If electrons themselves carry the usable energy, then when they move back toward the source, why would they not carry energy back as well? Yet in a working system, net energy flows from the plant to the load. The chain story cannot easily explain one-way energy flow with two-way charge motion. And that is where the deeper idea enters. Maxwell Poynting and the missing map of energy. In the 1860s and 1870s, James Clerk Maxwell pulled together a set of ideas that had been separate. He showed that changing electric fields and changing magnetic fields are tied together and that this tie produces waves. Light is one of those waves. In a light wave, the electric field and magnetic field oscillate at right angles to each other. They rise and fall in step. So when one is strongest, the other is also strongest. Maxwell's equations describe how that paired motion moves through space. A few years later, in 1883, John Henry Poynting asked a blunt question about conservation of energy. If energy is conserved in every tiny region of space, then energy must flow along some path that can be tracked. Sunlight makes the idea intuitive. During the minutes that light travels from the sun to Earth, the energy is not sitting in the sun or the Earth. It is stored in and carried by the fields of the wave as it moves. Poynting wrote down the tool for that tracking. The Poynting vector, usually written as S. Its size tells how much electromagnetic energy crosses a given area each second. In simple form, S equals 1 mho. The permeability of free space times the cross product tucked exp. The cross reduct points perpendicular to both fields. A right-hand rule gives the direction. Fingers along E curl toward B, and the thumb points along the energy flow. A simple circuit where energy travels outside the metal. Take a battery and a bulb connected by two conductors. Before the switch closes, the battery sets up an electric field. But with no steady current, there is no steady magnetic field and no power is delivered. Close the switch, and the circuit supports both kinds of fields. The battery's influence spreads through the circuit at nearly the speed of light, and the charge on the conductors shifts. Tiny excess charge collects on some wire surfaces, while other areas are slightly depleted. Inside the wire, that surface charge creates a small electric field that biases electrons to drift. The drift is slow, often around 1/10 of a millimeter s, even though the start signal is fast. That drifting charge produces a magnetic field around the wire. Now, electric fields outside the wire and magnetic fields outside the wire exist together. That is Poynting setup. So energy flow can be traced in the space around the conductors near the battery. The fields combined. So the Poynting vector points outward, as if energy is leaving through the battery's sides into the surrounding field. Along both wires, the same analysis shows energy moving from the source toward the bulb. At the filament, the Poynting vector points inward. Energy enters the bulb from all around it and becomes heat and light. Why alternating current? Still delivers one-way power? Replace the battery with an AC source. Now, the direction of current reverses every half cycle. Charges in the wire mostly jiggle back and forth over a full cycle. A given electron may end almost where it started. That fact often tempts people to say, so nothing moves. So how can anything be powered? The field picture answers cleanly. When the source voltage changes sign, the electric field in and around the conductors changes sign with it. The magnetic field created by the current also flips, because both E and B reverse together. Their cross-productive keeps pointing the same way for net energy delivery from source toward load. At any instant, the Poynting vector still threads its way through the space around the line and into the device where energy is dissipated as heat, light, or motion. This is why a household does not need electrons from a distant power plant. The wires already contain enormous numbers of charge carriers. The plant and grid equipment merely organize their tiny drifts and oscillations by setting up time-varying fields. Those fields propagate along the line and through the surrounding space, and the load extracts energy from them. The charges act like a medium that responds locally, not like parcels that must be shipped across a continent. The telegraph cable warning and the surprise answer. The field view is not just theory. Engineers ran into it when they tried to send signals through very long undersea telegraph cables. The first transatlantic cable laid in 1858 worked badly and did not last long. Pulses that began sharply arrived, stretched, and warped. Snorts, dots, and dashes blurred, so messages slowed to a crawl. A debate followed. One side pictured signals like water pushed through a soft tube. Another side argued that the real action was in the fields around the conductor and that the cable's environment shaped the result. Those arguments mattered because the cable was built like a sandwich. A copper core carried current. An insulator covered it. Then an iron sheath protected it. The sheath was meant to be mechanical armor, but as a conductor, it also changed the surrounding fields. It increased the effective capacitance and helped smear the pulses. The same logic explains why power lines are held high above the ground. Even damp soil conducts a bit, so air is used as a wide, insulating gap to keep the fields from coupling too strongly to the earth. Now return to the moon-long wires. When the switch closes, the field pattern updates and launches outward. The bulb is only 1 meter away through space, so the first change can reach it in about the time light crosses 1 meter, roughly 1 seconds, a few nancons. The long wires still matter for the exact voltage at first contact because they behave like transmission lines with a characteristic impedance. So the bulb may see only a fraction at first, then settle as waves reflect and redistribute. Different detailed models can give different transients, but the core point remains. The bulb begins to react almost immediately. Once the field view settles in, everyday power feels less mysterious. A power plant does not ship fresh electrons into a home. It nudges charges already in place, setting up changing fields that race outward and guide energy through space. The wires matter, but mostly as rails that shape those fields. That is why transformers can pass power across a gap. Why cable design changes distortion, and why a lamp can respond before any electron could travel far. The next time a switch clicks, picture energy flowing through the space around the wire. Fields quietly do the work, not charges. Asterisk, thank you so much for watching, all the way to the end. If you enjoyed this deep dive, please smash that like button, share your thoughts in the comments below, and don't forget to subscribe and turn on notifications so you'll never miss a future update.